Hi guys, welcome back to the basic VLSI series. In this episode, we're going to go and look into how we're going to simulate our CMOS circuit. That's this one over here that we came up with at the end of the last episode, and turn it into a Verilog file that we can then simulate on ModelSIM. All right. So that's basically what we're going to do here. So first of all, we need to label nodes that are not yet labeled. So for example, you have a few nodes here. You have a VDD up here. That's one node, so it's already labeled. You have a ground or VSS down here, this entire node all the way to here. And also there's a Z node that's also already there. But you have this middle node that's not yet been labeled. You have this node that's not yet been labeled. You have this in between A and B for NMOS not yet been labeled. You have this part not yet been labeled, and also this node between D and E also not yet labeled. So first of all, we need to label all these nodes. So let's do that now. All right, so now that we've labeled them, so what we need to do is in terms of creating the Verilog file. So we're going to use ModelSIM to create a new project. All right, so we're going to create a new project in ModelSIM. So we're going to call it by this name, called switch. All right, so everything I'm leaving at default. I have a particular folder here, so just click OK. And then I'll create a Verilog file, so I'm going to call that switch as well. So choose Verilog here and click OK. And also the test bench file. So you need a test bench file to actually do the simulation of our design. All right, so that's done. So we go ahead and create this file here. So we start with the module name. So we're going to call this. I'm going to call it by the same name that I've called the Verilog file. Now, our design. If I were to go back to our design, it has a B, C, D, E, F as input and a Z as output. All right, so we're gonna model that as the parameter. So the typical convention is to have the output as the initial parameters and the input as at the back. So I'm gonna call them as per what I had in the circuit diagram earlier. C, D, E, and F. All right, so basically I have, output, that is Z, and then everything else as input. All right, now I need to also define the bits that are in between the transistor. So that's the label that I put here. You know, P1, P2, N1, N2, and N3. These are the nodes that I've labeled that I need to then describe in Verilog. So I'm going to create few, wires. So I have P1, P2, N1, and N3. All right. I also need to define what considered, what signal is it? Is the high signal or logic 1 signal? So that's going to be labeled as VDD. And similarly, logic low, which I will label as VSS. All right, so then we have to go through the process of defining each transistor. Now, the format of defining each transistor is basically something like this. So we start with the particular type of MOSFET, so in this case PMOS, and then we give it a name, a device name, all right, a device name, all right, and then in parentheses we list out the drain, the source, and the gate nodes, all right. So similarly for, and a semicolon at the back. So similarly for NMOS, so again a device name for NMOS, all right, and again drain, source, and gate. So it's always drain, source, and gate. Now, but you need to understand that on the circuit side, if you look at these are PMOS, these are NMOS. So the source is actually at the top, all right. So for PMOS, the source is at the top because that is the source of for PMOS. The majority carriers will be holes, so the holes will come from VDD. So the source is at the top. For NMOS, the channel, the N channel is basically electrons as a majority carriers. So and the source is from ground or from VSS. So for PMOS, source is at the top, drain at the bottom, gate of course is on the left there. For an NMOS, source is at the bottom, drain is at the top, and gate again is on the left side. So basically in our Verilog, we define each and every one of these transistors in the drain source gate, where the drain source gate refers to the particular node label. So for example, if I want to model this PMOS transistor for signal A, then my code would be something like PMOS space and then maybe some kind of a device name, for example, P01, for example, and then brackets. Remember the order is drain, source, gate. So the drain is below here. So you're going to be, so I'm going to write P1, comma. All right, source is up here. So I'll say P1, comma VDD, comma, and then gate, which is A. All right, and similarly for, let's say, this NMOS here. So I would say NMOS space and then a name, let's say N06, for example, and then in brackets drain. Well, drain in this case is at the top, so it's going to be N3. Source is at the bottom, which is going to be VSS or whatever the signal I'm giving for ground, and finally gate is E. All right, so that's basically the order that you need to specify when you're creating a PMOS or an NMOS switch in Verilog. So let's just define this. Let me see if I can make this a bit smaller so I can have the image side by side. All right, so let's define each one of these. I'm going to basically define each transistor in the order of, A, B, C, D, E, F. All right, so let's start with the first one. So I'm going to call that P01. So the drain is at the bottom, so that's going to be P1. The source is at the top, so that's going to be VDD. And the gate is the input signal A. So that's PMOS, the first PMOS. And we'll continue on. So a different label. All right, so now we're talking about the B gate. So it's drain, source, gate. So drain is at the bottom, so P1 again. And then VDD again. That's the source. But now the gate is B. And we simply continue on like this. So now I'm talking about C. That's this PMOS gate over there. Sorry, PMOS transistor over there. So P03, drain, source, gate. So drain would be the bottom. So in this case, the output Z. And then the source is at the top. That's this node here, which is called P1. And finally, the gate. And so we continue on until we completely finish all the PMOS transistors. All right, so that completes all our PMOS gates. Now we continue on to our NMOS gates. So our first NMOS gate is going to be the one with input of A, so this one over here. So I'm going to call that N01. So again, it's drain source gate. So drain in this case is at the top, source is at the bottom, and gate is on the left. So drain is going to be Z, source is going to be N1, and finally gate is going to be A. And the same for the B, for the B gate. So N02, drain, so drain is at the top, so that's N1, source is at the bottom, which is VSS, right? And the gate is B. And we continue with the rest. Right, so that completes our module definition for the circuit that we've designed earlier. All right. So now let's do the test bench. Okay, before we do that, just a few reminders. Case is important. Case sensitivity is important. So you need to make sure that you, if you use lowercase, for example, here for wires, I'm using all lowercase. So make sure that when you're putting it inside, when you're defining it for your source or drain, for your PMOS or NMOS, make sure you stick to the same case. So here all lowercase. And for my signals, I typically use capital cases, so therefore, again, make sure they all follow the same thing. So again, VDD, VSS, they're all lowercase, so therefore, all the VDD and VSS are all lowercase. So that's really important. So now we've saved that. I'm just pressing Control S to save it. Now we're going over to the test bench. So just to recap in terms of what a test bench is. A test bench is what we use to simulate our module. All right. So let's just go ahead and do that. I explain as we create this. All right. So again, we start with the module. I'm going to call this switch TB by to keep the same name as the Verilog file that's over here, that Verilog file. So I'm keeping it by the same name. All right. So basically, in our test bench, in all outputs we define as wire. So I'll have a Z as my output, so I'll define it as wire, and all the inputs you have to define as registers. So I have 6 of them: A, B, C, D, E, and F. Now notice that I'm using exactly the same symbols and case as per my earlier definition in switch. Yeah, so capital Z and a capital A all the way to F. So in my test bench, I do the same. All right. Okay. So next, I need to instantiate my module. Instantiate means I want to now create the module and create it inside my test bench, if you like, the circuit under test. All right. So that's the name of my module, and I have to give it a label. So I'm going to call it SW. And then because I'm using the same signal letters and all of the same case, then when I'm defining the parameter, I can just simply say dot asterisk. I mean, otherwise I need to do something like this, where the list matches with the module definition that I had earlier, right? So this is the module parameter definition. So in my test bench, I would have to do the same. But then if the signals are all of the same case and same spelling, then this is a short form. I just say dot star, and it'll work exactly the same way. Right. So next is my simulation block. So I start with an initial begin. So what I want to do is I want to assign, A, B, C, D, E, F, all of them as basically a 6-bit register, where F is the most significant bit. So I'll list them in like this. All right. So by doing like this in curly brace in Verilog means I'm creating a bus. That means a multi-bit connection. In this case, 6 bits. All right. As a singular piece of variable, if you like. So if I say all this is equal to 0, that means I'm creating a 6-bit 0 value for each of these input signals. All right, so that means all of them will get 0. All right, so next I'll have my repeat block. Well, 6 is rather large in terms of if you want to simulate every single possibility. So I'm not going to do that. So I'm just going to show about 40 patterns. All right. And then after the initial application of all 0 at the input, after 5 period, simulation period, I'm then going to increment this bus, if you like, by 1. So let me just open up that space a bit. So I can simply say that plus 1. So this will increment the 6-bit bus as a singular 6-bit value. So it'll start from all the 6 bits being 0, and then it'll go to 1, 2, 3, and so on, and assigning each bit, assigning the value, if you like, to this batch of 6 signals, binary data. All right, and I'll end the repeat block, and I'll end the initial simulation module. So simulation block, and then I end the module. All right, so that's pretty much all I need to do in terms of wanting to simulate this. So if you notice, these files were just created, so next to the project panel here, it puts the status as question mark because it hasn't been compiled yet. So I go up here to compile all, press that, and it will go ahead and compile all the Verilog files that I have here. So if you notice here, there are no errors, so I get 2 green ticks to mean that there are no errors. So now I can actually simulate it. All right, I can actually simulate it. So I'm just making this side bigger. So I can click on this button here to start simulation. So I need to choose the test bench because in my project definition earlier, I chose work as the work area. All right, click OK. All right, so now I have all my signals here, so I can select them all. Well, once this settles, so I can select them all, yeah, or I can select one by one. So I can press Control A right now. Once I click inside this area, that will select all. All right, I can right click and choose Add Wave to actually add all of these highlighted signals as for my waveform simulation. All right, so or I can press Control W. So I'm going to do Control W. All right, so now what I can do is I can click on this button up here to run all, and it will do the simulation, and this is the result of that simulation. I can zoom into, because remember in my test bench I iterated only over 40 cycles, so it's not a complete thing because it can go on for quite a bit. But this is just to demonstrate a simulation. All right. Now you can go ahead and build a truth table from the original Boolean expression to confirm that the output is correct. All right. So I've done this earlier, so I know this output is correct. And that's basically how you can simulate using ModelSIM your switch level circuit. All right. Do comment and like if you like this video. If you have any questions, please put it down in comment, and see you all in the next part.